studying what is system software and what is the need to study system software and what are the components of various system software, we come to the assembler, okay, which is the second part of the first unit, assemblers. Here we are going to study what does an assembly level language program statements look like, how they can be classified, and finally we are going to study how to design a two-pass assembler. So beginning with elements of assembly language programming. When assembly level language programs came into picture, before them there were only machine level languages present. That is, programs were written in machine level language instruction. So you have an assembly level language which is obviously machine dependent, that is, it depends on the underlying architecture of the machine, and it is a low level language. Now as compared to a machine level language, it simplifies programming, and these are the three main advantages of writing an assembly level language program. First one is you don't need to memorize machine instructions, because to memorize machine instructions was a very tedious process, because it consists of binary numbers, zeros and ones. So it is very difficult to remember a series of zeros and ones. When you are going to use symbols in place of these numeric codes, it is easier to remember. In fact, you don't have to memorize any concepts, okay. So we use mnemonic operation codes which are called as opcodes. Operation codes is called as opcodes, and they are being used in place of machine instructions. So it basically eliminates the need to remember these these binary numbers, which usually stand for machine instructions. The second one happens to be the symbolic operands. That is, the memory binding to these symbols that are used are done by the assembler, and it is unknown to the programmer. Like if you used a subroutine like SQRT and that subroutine was associated with a particular symbol name, that linking, that is, that memory binding is done by the assembler itself. The programmer had no role in the memory binding. So the programmer virtually does not know how that memory binding is done. Okay, so in this case, in assembly level language programs, you have data and instructions associated with symbols, and those symbols are given their appropriate memory addresses by the assembler itself. It is not the task of the programmer. And finally, you can have data declared in a variety of notations. It need not be according to the architecture of the machine or the machine instruction set of the underlying machine. It can be in a variety of notations, and it is the job of the assembler to perform a required conversion. Whatever format is required, that format is actually converted by the assembler itself. Now we have how does an assembly level language statement format. Now this is the format of an assembly level language. Okay, the first one is a label. Anything that is written in square bracket happens to be optional, followed by the opcode. Then you have the first operand specification, and then you can follow it by an operand specification if required, right? So what does this label mean? It is basically a symbolic name, okay, and for that that symbolic name will be associated with a memory word, right? Then this opcode is nothing but your mnemonic opcode, like your add, sub, multiply, and this is the operand specification. Now this operand specification has this syntax. It is basically a symbolic name which can be followed by displacement and followed by register. Now these two are optional. You can only have a symbolic name, or you can have a symbolic name followed by displacement, and symbolic name followed by index register, or you can have a symbolic name associated with displacement and an index register. Now these are some of the examples. The first one simply shows a symbolic name area. So what it represents is one memory word in your memory that has been given or that has been associated with the symbol name area. What this represents is, this is the second format, symbolic name plus displacement. It represents that it is referring a memory word which is 5 places away from the memory word that is represented by the symbol area. Now this is area, that is basically a symbolic name, and this is the index register which is specified in simple bracket. This refers to a memory word whose address is obtained by adding the address referred by the symbol area with the contents of index register 4 to finally get your memory word. And this happens to be a combination of these two techniques, where the address referenced by this symbol name area is added with this constant 5, and that is then added with the contents of index register 4 to get the memory word we wish to reference. For our purpose, we use a simple assembly level language. This assembly level language happens to have the following format. We do not have this format. This is a general format of an assembly level language statement. Here in this statement, there will be two operands. There would be this label which is optional, there would be opcode, but here in place of operand specification, we are going to have two operands, and the first operand would always be a register. Okay, now the author has defined the 4 registers. It is the author's assembly language, the language given by the author itself. So the author has mentioned that there would be 4 registers which are represented by A register, B register, C register and D registers, and each is given serial numbers from 1 to 4 accordingly. That is, A register would have number 1, B register would be 2, C register would be 3 and D register would be 4. Now the second operand would basically be a memory word, okay, and it would be referenced using a symbolic name. Okay, in our simple assembly language, we are not going to use the indexing scheme. Okay, these are the mnemonic operation codes that are present for our assembly level language program. These are the instruction opcodes that are given for these mnemonics. Okay, for stop the code is 00, for add, sub, multiply it is 1, 2 and 3. Okay, and similarly for others. Now if we look at the mnemonic stop, it basically is asking the assembler to stop the execution, and it has an instruction opcode 00. Now when you look at these arithmetic operations add, sub, multiply, which are given numbers from 1 to 3, and division, which is given the instruction opcode 8. Okay, here all the arithmetic operations would be done in the register itself, and the final value would be present in the register itself. That is, if I say add and say 2 operands, the operation would take place in the register, the result would be placed in the register itself, and whenever you perform an arithmetic operation, a condition code will be set. Okay, now if you look at this in mnemonic, that which stands for move R, it basically means that we are moving contents into a registry. Okay, that is, we are moving a value in a memory word into a register. And if you look at move M, it means that we are moving certain contents into a memory word. Now that has an instruction opcode 05, and what does it mean? We are moving contents from the registry into that particular memory word. Now COMP has the instruction code 06, and it basically sets a condition code. Now BC is branch on condition, because we need to have conditional branching and unconditional branching statements in our assembly language programs. So we have this instruction BC, which is given the opcode 07. This is again an arithmetic instruction. Then we have read and print having opcode 09 and 10. Okay, the only difference here is these two differ from others, wherein here every statement would be having 2 operands, whereas only these two would, in which is this, these statements, in these statements you are not going to have the first operand being used.